Hello, everybody. My name is Jacob Chairs. I am the mentee. My mentor is Tiny Cheese, and I would like to present to you Number Fields and Class Number, a journey to understanding the Minkowski bound. Before we begin this talk, I would like to say I will be making comparisons to some of the stuff in linear algebra. It's just so that people without greater understanding of mathematics easy can follow along and have a better understanding of what I'm trying to present. Also, I will be presenting things more as a fact rather than proving them. And we're just going to be going through examples on how some of the theorems work or how some of the definitions look like. So let's begin. What is a number field? Strictly speaking, it is a finite extension of the field Q of the rational numbers and looks like Q alpha, where alpha is a root of some polynomial. If we were to make a similar comparison, imagine it as a finite vector space over Q generated by the roots of the polynomial. Example, Q square root of 2 is equal to the set A plus B squared root of 2, such that A and B are elements of Q. Recall the unique factorization theorem, where we can decompose any integer into the product of primes. This is a special property of the ring of integers. How does this correlate to number fields? So say we have a number field K. Well, we can find an integer ring called O of K in this number field. O of K is analogous to K. There are prime numbers in O of K, but O of K might not have unique factorization. For example, let K be Q square root of negative 5. Thus, we say O of K is Z square root of negative 5. Here we have the prime numbers 2 times 3 is equal to 6, but we also have different prime numbers, 1 plus square root of negative 5 times 1 minus square root of negative 5. That also gives us 6. Therefore, O of K cannot have unique factorization. Why is this, and how can we tell if O of K is close or far from having unique factorization? There is a term that describes this, and it is called class number. The class number of K is a whole number. If K has class number equal to 1, then O of K has unique factorization. It is hard to compute, but there are algorithms to bound it. Why and how? The class number of K is finite. This is a factorization algorithm. We will call it theorem 3.43 for now. Suppose that B is equal to A alpha, and let f of x be a minimum polynomial of alpha over K. Let P be a prime ideal in alpha. We will discuss prime ideals in a later slide. In A, choose monic polynomials g1x through grx in ax that are distinct and irreducible modulo P, and such that f of x is congruent to the product of gix ei modulo P. Then we have PB is equal to the product of ideals P comma GI alpha to the EI power is the factorization of PB into a product of powers of distinct ideals. What is a lower bound? The previous theorem can be a potential lower bound. It is hard to factor numbers in O of K. It is easier to factor ideals. What are ideals? Ideals are a subset I of a ring such that if AB is an element of I, then either A or B is an I. A similar comparison would be to see it as a subspace in K. Examples, the set of even integers in Z sub Q where I is equal to the ideal 2, which is the set A times 2, such that A is equal to A is not equal to A is an element of the integers. Another example is Z square root of negative 5, where the ideal 2 comma 1 plus square root of negative 5 is equal to the set n times 2 plus m times 1 plus square root of negative 5, such that n and m are elements of Z square root of negative 5, and this is an ideal. Let it be known it is easier to factor ideals into prime ideals. Class number measures how uniquely we can factor ideals into prime ideals. There exists a measure of size of the ideal, and it's called the norm. Now we're going to revisit 3.43 with an example, and this is to better understand how 3.43 works. So let alpha be a root of f of x, where f of x is equal to x squared plus 25x plus 5. I hope you guys know the quadratic formula, where alpha is equal to the following. K is equal to the span of q and alpha, and p is equal to 5. 5 of k is equal to the product of ideals 5 comma gi alpha to the ei. We notice that the polynomial mod 5 is congruent to x squared mod 5. Thus we have g1x is equal to x and e1 is equal to 2. By the theorem, we have 5 over k is equal to the product of ideals 5 comma alpha squared. What does this tell us? First, we have that CL of k is greater than or equal to 2. Why? Well, if CL of k is equal to 1, then 5 over k is just equal to the ideal 5, i.e. 5 has unique factorization. If phi over k is equal to the product of many ideals where none of the ideals are equal to the ideal 5 and the rest are ideals, then C of k cannot equal 1. What is the upper bound of the class number of k? Well, the upper bound can be given by the Minkowski bound, which is the following. Let k be an extension of degree n of q, and let delta k be the discriminant of k without q. Let 2s be the number of non-real complex embeddings of k. Then there exists a set of representatives for the ideal class group of k consisting of integral ideals a with the following inequality. The number on the right is called the Minkowski bounds. We sometimes denote it by b of k. The term ck is equal to the Minkowski bound without the square root of the absolute value of the discriminant of k. This is called the Minkowski constant. Now, there is known info about this constant, and this chart tells us what has been computed for the Minkowski constant, where n is the degree of the polynomial, r is the real embeddings, and s is the complex embeddings. Though there is a formula to get these numbers, and it's n equals r plus 2s, and basically they just ran through all the possibilities, and we have the following chart. Finding the discriminant is imperative to getting the Minkowski bound, and there is a formula for any to find the discriminant of any polynomial, but that is fairly uh, complex to grasp, and we are only going to be working with quadratic and cubic polynomials. Thus, I present to you the discriminant of those following polynomials, which is dq is congruent to the discriminant of a quadratic is congruent to b squared minus 4ac, and the discriminant of a cubic is congruent to 18abcd minus 4b cubed d plus b squared c squared minus 4ac cubed minus 27a squared d squared, and that's for cubic. It's quite the mouthful, but necessary. Now the following examples are z square root of negative 5 sub q square root of negative 5. Here we have the discriminant is negative 20. How the corresponding polynomial to this field is x squared plus 5 with the quadratic, uh, the formula we have for the discriminant of a quadratic, we get that it's negative 20, and the Minkowski constant is 0.636 given by the chart. Thus, by the theorem, we have the following inequality. 0.636 times square root of 20 is equal to 2.8. We got square root of 20 because remember the discriminant of k is in this formula it would be the absolute we would square root the absolute value of the discriminant, and thus we would get the following inequality, and we have that it is bounded above by 3, and by the previous theorem 3.43 we have that the class number of this field is greater than or equal to 2. How? Well, by similar logic of the example we had for theorem 3.43. Thus, we have that the class number of this field is equal to 2. Why? Well, it is bounded below by 2, and it can be greater than or equal to 2. But we have that it's strictly less than 3. Thus, we have only one possibility, since the class number has to be a whole number, which is class number equal to 2. Now, let K be a cubic field with a discriminant less than 0. Here we have the Minkowski constant is 0.283 given by the chart. If we want unique factorization in this field, we need the upper bound to be 2, such that the following inequality holds. And with a little bit of algebraic manipulation, we conclude that the discriminant needs to be the absolute value of the discriminant needs to be less than or equal to 49, or more concretely, we have to have the discriminant is greater than or equal to negative 49 and less than 0. A cubic that satisfies this inequality is x squared plus 1, where the discriminant is equal to negative 27. Let K be a cubic field with a discriminant greater than 0. Now here we have the Minkowski constant is 0.222 given by the chart. If we want unique factorization of the field, it has to be bounded above by 2. Thus we have the following inequality, and by similar algebraic manipulation, we conclude that delta K, the absolute value of delta K, needs to be less than or equal to 81, or more concretely, 81 has to be greater than or equal to delta K, which is greater than equal to, not greater than or strictly greater than 0. A cubic that satisfies this inequality is x cubed plus x, where the discriminant of K is equal to 16. That concludes my talk. Thank you for listening. Here are some open questions for you to consider. Are there easy bounds for quartic fields? Are there easy bounds for any nth polynomial fields? Thank you. Have a very nice day, and I hope you guys stay healthy and well.